Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 15. In this lecture, we'll discuss shock waves. This topic is covered in Chapter 17 of our textbook by Surway and Jowett. Recall from our previous lecture that the Doppler effect is essentially the result of motion of the source or motion of the detector. In this context, the source refers to whatever is generating or producing or broadcasting the waves, and the detector refers to whatever is perceiving or receiving or hearing the waves. The exact relationship between the frequency at detector and the frequency at source is given by the Doppler formula, which I've written here in the notation that I tend to use. However, note that the authors of our textbook use a slightly different notation. The Doppler effect ultimately is in part the result of the fact that the separation between the wavefronts changes when the source is moving. So when the source is moving in a particular direction, in front of the source, the separation between the wavefronts becomes smaller. That means that the wavelength becomes smaller, which in turn implies that the frequency detected by a detector must increase, as dictated by this equation here. Behind the source, on the other hand, the separation is increasing. Remember that the separation between two of these circles is the wavelength. Therefore, the separation is increasing, the wavelength is increasing, and consequently the frequency that is detected behind the source must decrease. It turns out that this change in the separation between wavefronts is not just responsible for the Doppler effect, it's also responsible for a different phenomenon known as shock waves. To understand shock waves, you might want to ask yourself what happens if the speed of the source continues to increase. So consider a source that's going faster and faster and faster. Eventually, the source speed will reach the speed of the sound waves. What happens at that point? You can already see that the Doppler formula runs into problems. If the source speed is equal to the wave speed, then the denominator becomes 0 and the fraction becomes indeterminate. So the Doppler formula is really not valid for situations where the source speed is equal to the wave speed. We didn't precisely derive the Doppler formula, however, the derivation is simply not valid for any case where the source speed is greater than c. This equation is valid only when the source is moving more slowly than the waves themselves. When the source begins to move at the wave speed or faster, then we have shock waves. To understand shock waves, let's consider a simple animation. We've seen this animation before. What we have at the center is a source of sound waves, and on the left and on the right we have two detectors. We've already seen what happens when the source moves slower than the speed of sound. What we get is the Doppler effect. We now want to see what happens when the source moves at or faster than the speed of sound. So to begin with, let's consider what happens when the source moves at the speed of sound. As you can see, the source remains on the very front of the wavefronts. After all, it's moving with the same speed as the wavefronts. And something interesting is happening. The wavefronts seem to bunch up on top of each other, at least in front of the source. Let's speed things up a little bit. Now the source is moving 20% faster than the speed of sound. Again, you can see this region where the wavefronts are overlapping, where multiple wavefronts happen to be at the same place and at the same time. This effect of overlapping wavefronts becomes even more prominent when we move even faster. Here, the source speed is moving at 1.4 c. It's clearly staying ahead of the waves, so it's outrunning the sound waves. And behind the source, there's now this triangular region where on the boundaries multiple wavefronts are overlapping. I'm describing this shape behind the source as triangular, but of course in three-dimensional space this would be a cone. So if you imagine that the blue space is air and that the source is an airplane, let's say a supersonic jet, then this triangular region behind the jet would basically be a cone. We can make the source go even faster and the effect becomes even more prominent. At 1.6 C, there's now clearly a conical region behind the source, and on the edges or the boundaries of this conical region, we have many overlapping wavefronts. This overlapping region is known as a shock wave. Recall that these wavefronts represent peaks of the wave. In particular, they represent points where there is a maximum displacement of the air molecules. Now, as one wavefront passes through a region, the air molecules in that region begin to oscillate. In particular, they oscillate with maximum displacement as this particular wavefront passes through. Now, you need to wonder what happens when there are 2 or 3 or 4 overlapping wavefronts. If one wave moves the molecules by, let's just say 1 millimeter, then 2 waves will move them by 2 millimeters. 3 waves would move them by 3 millimeters. So overlapping multiple wavefronts results in very large displacements of the air molecules. These very large displacements of the air molecules correspond to very large sounds. This very loud sound is exactly what's known as a shock wave. So let's summarize the discussion on the previous slide. When the source speed exceeds the wave speed, so when V sub s is greater than or equal to c, wavefronts begin to overlap in certain locations. When these wavefronts overlap, they result in larger amplitudes. In particular, the air molecules begin to move much larger amounts than usual. The overlap region is shaped like a cone. In pictures on the screen, they might look like triangles, but of course in three-dimensional space, they are cones. The motion of this cone is referred to as a shock wave. Shock waves can happen for all kinds of waves. We're talking about sound waves here, but in general, you can have shock waves produced by water waves or electromagnetic waves. However, when shock waves occur in the context of sound waves, they are usually referred to as a sonic boom because the shock wave is often heard as a very loud sound. In this picture here, as the person looks up at the sky and sees this supersonic jet fly overhead, he does not hear anything until the conical region behind the airplane arrives at his location. Right on the edge of this cone is where the sonic boom is located. So for that fraction of a second, he's going to hear a very loud sound as the airplane passes overhead. So far, our discussion of shock waves has been somewhat qualitative. However, one important quantitative result that you need to be aware of is this equation here. In discussing shock waves, people are often interested in how wide the shock wave cone is. In particular, they want to know what the opening angle of this cone is as the source moves faster than the speed of sound. It turns out this opening angle is actually reduced the faster the source moves. A little more precisely, angle theta is given by this equation here. Note that theta is not the full opening angle of the cone, it's half of the full opening angle. It's known as the half angle. C, of course, is the speed of sound, and V sub s is the speed of the source. You can see the shape of the shock wave cone that forms behind a supersonic source in this picture here. What we have here is a jet aircraft that is moving faster than the speed of sound, and behind it we see what is known as a vapor cone. A vapor cone is basically the condensation of moisture that is naturally present in air. The formation of a vapor cone by itself does not necessarily indicate supersonic speeds. So a vapor cone can also form when the aircraft is traveling slower than the speed of sound. However, the shape of the vapor cone indicates the shape of the cone that we've been discussing here. The half angle of this cone can be calculated using this formula. One of the first people to seriously investigate shock waves was the Austrian physicist and philosopher Ernst Mach. In his honor, people often speak of the Mach number. The Mach number is used to characterize the speed of supersonic sources. The Mach number is defined as the speed of the source divided by the speed of the sound. This half angle here is sometimes referred to as the Mach angle, and by inverting this formula on top, you can see that theta is simply the arcsine of c over vs, which is the reciprocal of the Mach number, so we can say that theta is equal to arcsine of 1 over m. So let's end this lecture with a practice problem. The SR-71, also known as the Blackbird, is the fastest airplane ever made as a production model. So there have been faster airplanes, but they were made as experimental or one-off models. The aircraft is capable of achieving Mach 3.2. What that means is that the aircraft is capable of traveling at 3.2 times the speed of sound. Calculate the half angle of the shockwave cone at that speed. Well, recall that the sine of the half angle is equal to the speed of sound divided by the speed of the source. In this case, the speed of the source is 3.2 times c. That's what Mach 3.2 means. Crossing out the two c's, we find that sine of theta is equal to 1 over 3.2. We can take the arcsine, which I've written as a sine here, of both sides, and we find that the half angle is equal to 18.2 degrees. Hopefully from this calculation, you can see that the faster the aircraft goes, the smaller theta will be. In some sense, the cone closes in on itself the faster the aircraft moves. And that is the end of this lecture. Thank you for your attention.